What if the first civilization on Earth did not rise beside the Nile, the Tigris, or the Indus, but on a world that no longer exists? A single supercontinent stretching from pole to pole, where every landmass touched and every ecosystem connected. In that world, there were no oceans separating cultures, no isolated continents slowing the spread of ideas. If intelligence sparked there, it would have had the entire planet as one continuous stage. Trade, migration, knowledge, nothing would be geographically trapped. A civilization born on Pangaea would not grow in pockets. It would spread like a living network across one vast land bridge, shaping climate, ecosystems, and even geology on a planetary scale long before humans ever appeared. The real question isn't whether their cities survived, it's whether the planet itself still bears the imprint of what they did. Before we dive deeper, ignite that like button and prepare for the revelations to come. Tell me in the comments where you are listening from, what time it is there. And as always with our videos, the visuals are here to add context, but they aren't necessary to follow along. Thank you for always having our back. Prepare yourself, and let's dive in. Rock remembers pressure, not footsteps, and oceans remember depth, not the names of shores that sank beneath them. When continents collide, stone folds like fabric, mountain ranges rise, and entire landscapes vanish into Earth's interior through subduction, the slow swallowing of crust back into the mantle, like a conveyor belt recycling the planet's surface. Over hundreds of millions of years, this process grinds civilizations, if any existed, into minerals, heat, and silence. The planet is not a museum, it is a furnace with tides of stone. That simple fact reshapes how we think about the deep past. Absence of ruins does not equal absence of builders. It may simply mean the builders lived too long ago for their world to survive the geological grinder. About 335 million years ago, nearly all major land masses locked together into a supercontinent we now call Pangaea, a word meaning all Earth. Imagine standing on a shoreline where waves from a single global ocean, Pangaea, crashed against cliffs that today lie on different hemispheres. Africa pressed against South America, North America leaned into Europe. Antarctica rested not as an icy wasteland but as part of a vast southern expanse with forests and river systems. Climate behaved in extremes, interior regions far from moderating ocean air, baked into mega-deserts larger than the Sahara. Coastal belts, however, formed long ecological corridors, humid, biologically rich, and connected without the barriers of wide seas. For life, that meant migration without interruption. For intelligence, if it emerged, it meant ideas could travel as freely as animals. Official timelines place intelligent tool-using humans at a very recent sliver of history, with complex societies rising only after the last ice age. Yet intelligence itself is not tied to one body plan. Evolution is not a ladder, but a branching bush. During the Carboniferous and Permian periods, oxygen levels climbed as high as 35%, compared to today's 21%. In such air, metabolism, the chemical engine inside cells, runs hotter. Giant insects with wingspans like hawks and millipedes, longer than a car, existed because oxygen diffused more easily through their bodies. When environments push biological systems into unusual ranges, novel structures appear. Neural complexity, the density of connections that allows learning and memory, could have followed paths we do not recognize in fossils at a glance. Fossils preserve hard parts best: shells, bones, teeth. Brains, culture, language leave almost nothing. Even our own technological layer, sometimes called the Anthropocene signature, would blur with time. Plastics would break down into microscopic fragments, metals would oxidize into ordinary ores, and skyscrapers would collapse into sediment. Future geologists might find a thin band enriched in unusual alloys and isotope ratios, like a faint pencil line across a thick book, and argue about its cause. Stretch that thought across 250 million years and the line nearly vanishes. The ocean floor complicates the picture further. Most seafloor is younger than 200 million years because it forms at mid-ocean ridges, where magma rises and cools and is later consumed at subduction zones. Any coastal settlements built along Pangaea's margins could now lie on crust that no longer exists, recycled into mantle convection currents, slow churning flows of semi-molten rock that drive plate tectonics. We have explored only a fraction of modern seabeds. The ancient ones are gone entirely. What survives are fragments welded onto continents, called terranes, like patches sewn onto a jacket. Interpreting those fragments is like reconstructing a shattered mirror without knowing the original reflection. Occasionally, anomalies appear. Stone formations underwater show terraces and right angles that resemble architecture, yet geology can carve straight lines through jointing, the natural cracking of rock under stress. Metallic spheres turn up in ancient strata, and critics argue over whether they are concretions, minerals crystallizing in layers around a core, or artifacts shaped by intention. Each case invites caution. But the broader question remains, how would we distinguish design from deep-time geology when both operate under immense pressure, heat, and scale? Mass extinctions add another layer. Around 252 million years ago, the end Permian event erased up to 90% of marine species. Massive volcanic outpourings in what is now Siberia released greenhouse gases, warming oceans, reducing oxygen, and acidifying water, a chemical shift that dissolves shells like vinegar on chalk. Ecosystems collapsed. If a technologically active species had existed then, its population centers along coasts would have faced rising seas, toxic air, and ecological chain reactions. Infrastructure depends on stable climate. Remove that, and complexity unravels quickly. Collapse leaves little time for preservation. Yet patterns in geology sometimes echo industrial effects we know today. Rapid carbon isotope shifts, sudden sediment layers rich in certain metals, abrupt biodiversity loss. Natural explanations exist: flood basalts, asteroid impacts, methane releases. Still, the thought experiment matters. If an earlier civilization burned fuels, mined ores, or altered chemistry, its fingerprint might resemble known natural disasters. We could be reading a palimpsest, a manuscript scraped and overwritten, where original text lingers faintly beneath newer ink. Pangaea's geography would have shaped any such society. With land continuous, trade routes could span thousands of miles without ships. Cultural divergence might slow, technological diffusion accelerate. Coastal climates, moderated and biodiverse, would favor stable settlements. Interior deserts, harsh but resource-rich, could drive innovation in water management, metallurgy, or energy use. Over millions of years, far longer than our own civilization's brief sprint, development might reach levels we struggle to imagine, not necessarily through steel and silicon, but through materials and methods adapted to their biosphere. The deeper we look, the more history resembles a book missing most of its pages. What remains are marginal notes, mineral anomalies, strange formations, mythic echoes of worlds destroyed by flood or fire. Whether those notes point to a vanished intelligence or only to nature's vast creativity is still uncertain. But the scale of time, the violence of geology, and the fragility of evidence force a humbling possibility. Entire chapters of planetary history may have unfolded, flourished, and been erased, leaving us to read between lines of stone. Stone does not only rise and fall, it also drifts, fractures and heals, and in those slow movements clues hide like scars beneath skin. When Pangaea began to crack apart around 200 million years ago, the rupture was not a single violent split, but a drawn-out tearing, magma welling up along seams, new ocean basins opening like wounds that never fully close. The Central Atlantic magmatic province, an immense outpouring of lava that stretched across what would become 4 continents, covered millions of square kilometers in basalt, dark volcanic rock that cools into vast, layered plains. These eruptions released gases that altered climate, dimmed sunlight with aerosols, and stressed ecosystems already balanced on narrow margins. It was not one explosion but a pulse lasting hundreds of thousands of years, long enough for a civilization, if present, to watch its world change generation by generation. Basalt floods behave like liquid, stoned seas. They bury landscapes under kilometers of rock, sealing whatever lies beneath. In rare cases, footprints of animals have been found preserved in volcanic ash that later hardened, as if time briefly paused to take an impression. If an earlier intelligent species existed, entire settlements could be entombed this way, locked beneath layers that now resemble natural plateaus. Detecting artificial structures under such thickness would require seismic imaging, the use of sound waves to map underground features, the way medical ultrasound maps a body. We use it today to find oil and fault lines, but scanning every ancient volcanic province at high resolution is far beyond current effort. Another archive lies in isotopes, subtle variations of elements that act like chemical timestamps. Carbon, for instance, exists mainly as carbon-12 and carbon-13. Living organisms prefer the lighter form, so massive biological activity leaves a signature in rocks. When we burn fossil fuels, we shift this ratio measurably. In deep time, similar abrupt shifts mark crises like the Paleocene-Eocene thermal maximum, a rapid warming event 56 million years ago. Natural methane releases are the leading explanation, but the pattern, fast warming, ocean acidification, species turnover, mirrors what industrial activity could produce. The resemblance does not prove design. Nature can be just as extreme. Yet it shows that industrial-scale effects are not invisible in stone. They linger as chemical whispers. Consider metals rare in Earth's crust but common in technology: iridium, platinum, osmium. These elements often signal asteroid impact because meteorites carry them in higher concentrations. The famous iridium layer at the boundary that marks the extinction of dinosaurs is one such example. But advanced industry also concentrates rare metals. Over millions of years, corrosion and sedimentation would smear these traces into thin global layers. A geologist might catalogue them as extraterrestrial dust or volcanic byproduct. Interpretation depends on expectation. If no one imagines industry in the deep past, no one labels the anomaly that way. Magnetic minerals offer another memory. When lava cools, tiny crystals align with Earth's magnetic field, freezing a record of its direction. By studying these orientations, scientists reconstruct continental drift and past pole positions. Yet magnetic stability during certain intervals, like the long superchron of the Permian, raises questions about the core's dynamics. Could surface processes influence the field? Today we know solar storms and human-made currents can disturb it locally. A civilization with mastery over electromagnetism, power grids on a planetary scale, might leave subtle disturbances, though separating such effects from natural variation would be nearly impossible after tectonic reshuffling. Water also archives stories. Sedimentary rocks formed in lakes and seas stack like pages, each layer capturing grains, shells, and chemistry from its time. Within these layers, sudden appearances of synthetic-like molecules would stand out, compounds with structures rare in nature. Our plastics, pesticides, and long-chain polymers fall into this category. Given enough time, most would degrade, but some molecular fragments might persist as unusual organic residues. Future chemists could detect them, much as we detect traces of ancient lipids from microbes billions of years old. The challenge lies in recognizing them as products of intention rather than exotic biology. Climate belts on Pangaea shaped erosion and preservation. Arid interiors favored wind-blown dunes that later hardened into sandstone, preserving cross-bedded patterns like frozen waves. Humid coasts built thick coal swamps, burial grounds for plant matter that became fossil fuel. If intelligent beings exploited such fuels, mining scars might once have marked the land, but erosion rounds edges, sediments fill pits, and vegetation reclaims surfaces. After tens of millions of years, a quarry becomes a gentle valley. A road becomes a faint alignment of minerals indistinguishable from natural veins. Biology might carry indirect signs. Rapid bursts of diversification sometimes follow extinctions, as if ecological niches suddenly open. This happened after the Permian and again after the dinosaurs' demise. Natural recovery explains much, yet the idea that prior life-engineered environments, selectively breeding species or transporting organisms, adds another layer to consider. Humans already move species across continents, creating biogeographic puzzles. In deep time, such patterns would blur, but sudden appearances of species far from evolutionary relatives might raise eyebrows. Ultimately, the search for ancient intelligence on Pangaea is less about finding a lost city than about learning to read subtlety. We look for cities because our minds think in walls and towers. But time dismantles geometry first. What survives are shifts in chemistry, odd distributions of elements, abrupt ecological turnovers, patterns that resemble fingerprints smudged across stone. Whether those smudges belong to nature's own vast machinery or to forgotten hands remains unresolved. The planet keeps its secrets well, not out of malice, but because its memory is written in processes slower and more powerful than anything built on its surface. Far below the reach of sunlight, the sea floor stretches like a second planet, mapped in fragments, imagined in the gaps. Modern sonar, sound pulses sent into the depths and timed by their echoes, has revealed mountains taller than the Alps, valleys deeper than the Grand Canyon, and plains so flat they resemble poured concrete. Yet over 80% of this terrain remains poorly resolved. During the age of Pangaea, coastlines traced different shapes, and vast tracts of what is now deep ocean were once dry land, river deltas, and shallow seas rich with life. When sea levels rose and plates shifted, those regions drowned, carrying with them whatever ecosystems or constructions existed along their margins. Water, cold and dark, can preserve as well as erase. Stone structures submerged today often appear sharper than those on land because waves, rather than wind and rain, dominate their erosion. In some places, divers report stepped formations, right angles, and flat terraces that resemble platforms. Geologists point out that sedimentary rocks fracture along bedding planes, creating blocky shapes. Jointing, natural cracks formed as rock cools or compresses can intersect at near-perfect angles. The debate illustrates a core problem. The human eye recognizes patterns quickly, sometimes too quickly. Pareidolia, the tendency to see familiar shapes like faces in clouds, also operates at geological scales. Still, pattern recognition is how discoveries begin. The key lies in testing whether geometry aligns with known physical processes or resists them. Underwater preservation has a precedent. Entire Bronze Age towns now rest beneath Mediterranean bays, their walls intact after thousands of years. Multiply that preservation window by colder temperatures and low oxygen, and decay slows further. Organic materials like wood rarely survive millions of years, but stone foundations might, especially if buried quickly by sediments that seal them from currents. River deltas are particularly good at this. They dump layers of silt during floods, entombing surfaces much as Pompeii was buried by ash. If coastal settlements existed during late Pangaea, some could lie beneath thick sediment blankets offshore. Seamounts, underwater mountains formed by volcanic activity, sometimes carry flat tops called guyos. These plateaus were once islands planned down by waves before subsiding. On their surfaces, coral reefs fossilize, forming limestone caps. If intelligent life occupied such islands, rising seas would have submerged them gradually. Over time, coral growth could cover artificial features like a living skin. Coral limestone, porous and soft, dissolves and recrystallizes, obscuring shapes beneath. Distinguishing a carved block from a reef framework after hundreds of millions of years would challenge even careful analysis. Technology leaves different marks underwater. Mining operations disturb sediments, creating plumes that settle as unusual layers. Smelting, extracting metal from ore, produces slag, a glassy byproduct with chemical signatures distinct from natural volcanic glass. Slag fragments have been found near ancient human sites. Over deep time, slag would weather, but its composition enriched in certain oxides might remain detectable. Hydrothermal vents where seawater heated by magma circulates through crust naturally concentrate metals like copper and zinc. An advanced society might exploit such sites, leaving patterns of excavation or altered mineral ratios. Acoustic anomalies occasionally surface in marine surveys, regular ridges, grid-like arrangements, or linear mounds. Most resolve into sediment waves shaped by currents or tectonic fault lines. Yet the possibility that some represent buried structures persists at the edges of interpretation. Confirmation would require drilling cores and direct sampling, an expensive and technically demanding task. Ocean research budgets prioritize climate, fisheries, and hazard studies, leaving little room for speculative archaeology on geological timescales. Microfossils add another thread. Foraminifera, tiny shelled organisms, record ocean chemistry in their calcium carbonate tests. Their isotopic ratios reveal temperature and carbon cycles. Sudden anomalies might indicate rapid environmental shifts. If a prior civilization altered oceans through runoff, pollution, or large-scale engineering, microfossil records could capture the disturbance. Today's human impact already registers in such proxies. Extrapolate millions of years, and the signal fades but may not vanish entirely. Tectonic recycling, however, erases much. Oceanic crust older than about 200 million years is rare because subduction drags it down. Any truly ancient coastal remains on oceanic plates likely no longer exist at the surface. Only fragments scraped off and plastered onto continents, called accretionary wedges, survive. These chaotic mixtures of rock resemble geological junkyards, blocks of varied origin mashed together. Within them, unexpected fossils sometimes appear, transported far from where they formed. An artifact caught in such a wedge could surface in a mountain belt millions of years later, divorced from context. The psychological dimension matters too. Researchers trained in conventional timelines may unconsciously filter out interpretations that suggest extreme antiquity for complex behavior. Scientific caution is necessary. Extraordinary claims demand strong evidence. Yet paradigms shape which questions are even asked. If surveys never look for deep-time cultural signatures, they will not find them. Expanding search criteria does not require abandoning skepticism, only widening the net of possibilities. Deep oceans, then, function as both vault and shredder. Cold, pressure, and sediment can lock details in place, while tectonics and chemistry dissolve others beyond recognition. The silence of the abyss does not mean nothing ever stood along its vanished shores. It means the record, if present, lies scattered in fragments, disguised as geology, waiting for methods subtle enough to read intention in layers of stone and salt. Ice looks lifeless from above, a white desert stretching beyond the curve of the horizon, yet beneath Antarctica's frozen shield lies a landscape older than many mountain chains now exposed to air. Radar pulses fired from aircraft penetrate the ice and bounce back from rock below, tracing hidden ridges, valleys, and basins. The result is a ghost continent complete with river systems and lakes sealed under kilometers of pressure. During the time of Pangaea and later Gondwana, Antarctica did not sit locked at the pole under perpetual cold. It drifted through temperate latitudes, hosting forests of Glossopteris trees, seed ferns with tongue-shaped leaves that formed dense ecosystems along rivers. Fossils of these plants appear across Africa, India, Australia, and South America, evidence of a once connected world. Where forests grow, soils develop. Where soils develop, life builds complexity. Burial under ice can act like a time capsule. In Greenland, entire landscapes have been found preserved beneath the ice sheet, including ancient soils and plant remains. Antarctica's ice, in places more than 4 kilometers thick, exerts immense pressure that seals subglacial environments from surface disturbance. Lake Vostok, one of the largest known subglacial lakes, lies under such pressure that the ice above behaves almost like rock. Water there remains liquid due to geothermal heat rising from Earth's interior and the insulating blanket of ice above. Microbial life has been detected, surviving in darkness, feeding on chemical gradients rather than sunlight. If microorganisms can persist, stone structures or shaped materials might as well, protected from weathering by isolation. Glacial motion complicates preservation. Ice flows slowly like very cold syrup, grinding rock beneath it into fine powder called glacial flour. Over millions of years, this movement scours surfaces, carving grooves known as striations. Yet not all regions move equally. Some subglacial basins remain relatively stable, shielded by bedrock highs. In such pockets, erosion slows and sediments accumulate, Layers build quietly, like dust in an attic no one enters. If remnants of past surfaces exist there, they could lie buried but intact, beyond the reach of grinding ice. Magnetic surveys over Antarctica reveal anomalies, regions where the magnetic field deviates from expectation. Most correspond to variations in rock type, such as iron-rich formations, but occasionally patterns appear linear or geometric at scales that spark curiosity. Straight lines in geology often signal faults, fractures where crust has shifted. However, distinguishing between tectonic fractures and artificial alignments requires high-resolution data rarely available under ice. The challenge is not only technical but interpretive. Natural processes can produce surprising regularity. Meteorites accumulate on Antarctica's surface because dark stones stand out against white ice and are preserved in cold dryness. Researchers have collected thousands, providing insight into early solar system history. If extraterrestrial rocks can survive, terrestrial artifacts might too, though likely deeply buried. The analogy underscores how unusual environments can safeguard materials far beyond their typical lifespans. The continent's isolation began when Antarctica separated from Australia and South America, allowing the Antarctic circumpolar current to form, a ring of water isolating it thermally, leading to glaciation. Before that, rivers flowed, sediments spread across plains, and coastal margins teemed with life. A coastal civilization in such an era would have faced gradual cooling, shifting habitats and encroaching ice. Retreat inland or migration north might follow. Abandoned settlements could become entombed as snow accumulated year after year, compressing into ice that locked them away. Drilling through ice is slow and expensive. The borehole to Lake Vostok took decades, using kerosene-based fluids to prevent collapse. Contamination is a constant concern. Introducing modern microbes could ruin pristine ecosystems. These difficulties limit exploration to small areas. Vast sectors remain untouched, their subglacial geology inferred rather than seen. Satellite gravimetry, measuring tiny changes in gravitational pull, hints at buried mountain ranges like the Gamburtsev Mountains, comparable in scale to the Alps yet unseen by human eyes. Mountains imply erosion, rivers, and sedimentary basins, places where traces of past surface activity could hide. Sediments under ice may hold pollen grains, spores, and microscopic charcoal from ancient fires. Such particles tell of vegetation and climate. Anomalous concentrations of metals or unusual mineral processing residues within these sediments could signal human-like or non-human technological activity. Extraction of cores from subglacial basins might one day reveal layered histories spanning millions of years, like reading rings of a tree that grew in darkness. Psychologically, Antarctica represents the unknown edge of the map, a place where speculation thrives because access is limited, yet restraint is essential. Natural explanations account for most anomalies. Still, the combination of former habitability, long-term burial, and minimal disturbance makes the continent a compelling archive of deep time. If any land-based traces of ancient intelligence escaped erosion elsewhere, the southern ice may conceal them, not as gleaming cities, but as altered soils, shaped stone, or chemical signatures waiting beneath frozen silence. In that silence, pressure replaces wind, and darkness replaces day. The ice records snowfall like pages stacking upward, each layer trapping air bubbles that preserve ancient atmospheres. Those bubbles tell us carbon dioxide levels, volcanic eruptions, and temperature shifts. They do not yet tell stories of culture, but they prove that even air can be archived for hundreds of thousands of years. Extend that principle downward into the bedrock and sediments, and the possibility emerges that deeper chapters of planetary history rest sealed, patient as stone, beneath a continent that once bloomed green under a different sun angle. Not all memory is written in stone. Some of it travels inside stories carried by voices long before ink, like embers passed from one fire to another. Myths are often treated as fantasy, yet they function as cultural storage systems, compressing information into symbols, images, and narrative patterns that survive upheaval. A flood becomes a god's anger, a comet becomes a dragon, a lost homeland becomes a paradise sunk beneath the sea. When continents shift and coastlines drown, people move, but stories move with them. Over generations, details blur, but core impressions, catastrophe, migration, a former age of greatness, can persist for astonishing spans of time. Across the world, traditions speak of worlds destroyed and renewed. Mesopotamian epics describe a deluge survived by a single prepared figure. Biblical texts echo the motif. In India, cycles of ages called yugas describe long eras of decline and renewal, with vast timescales that dwarf ordinary history. Mesoamerican accounts speak of previous suns, earlier creations erased before the current one. These parallels do not prove shared events, yet they hint at collective attempts to frame deep memory in human terms. When ice melted at the end of the last glacial maximum, seas rose over 100 meters, swallowing coastal plains where early communities lived. For those people, the sea's advance would have felt like the end of the world. Oral traditions have demonstrated surprising longevity. Australian Aboriginal groups preserve stories describing coastlines that existed more than 7,000 years ago, before rising seas reshaped the land. These narratives mention islands now submerged and pathways once walked across dry ground. Geological surveys later confirm those ancient shorelines. The mechanism is simple yet powerful. Embedding geography in sacred narrative ensures careful transmission. If memory can persist for millennia, speculation asks whether fragments might echo even older environmental shifts, stretched and mythologized beyond recognition. Descriptions of advanced beings or teachers from a prior age appear in many traditions. Sumerian Apkallu, often depicted as sages emerging from the sea, brought knowledge of writing and crafts. Mesoamerican culture heroes like Quetzalcoatl and Viracocha arrive after catastrophe to teach agriculture and order. In Greek myth, Prometheus gifts fire, symbol of technology, to humanity. These figures blur the line between divine and cultural memory, perhaps encoding the idea that knowledge survived disaster through a few carriers. Some texts go further, describing technologies in symbolic language. The Indian epic Mahabharata recounts weapons producing light like many suns and winds that wither life. Interpreters debate whether these are poetic metaphors or echoes of phenomena beyond ancient understanding. The Sanskrit term vimana refers to flying chariots or palaces moving through the sky. Similar motifs, skyboats, fiery wheels, appear in other cultures. Human imagination certainly dreams of flight, yet repeated mechanical detail invites curiosity about whether such imagery preserves distorted recollections of lost capabilities or simply reflects universal aspiration. Astronomical knowledge encoded in myth adds another layer. The Dogon people of Mali possess traditions about a dense companion star to Sirius, matching the existence of Sirius B, a white dwarf discovered with telescopes in the 19th century. Debate continues over whether this knowledge predates contact with modern science. Meanwhile, ancient structures worldwide align with solstices, equinoxes, and star risings. Tracking slow celestial shifts like the precession of Earth's axis, a 26,000-year wobble, requires long-term observation. If such knowledge appears suddenly in the archaeological record, it suggests inheritance from earlier observers. Maps present similar puzzles. The Piri Reis map of 1513 shows parts of the South American coast with striking accuracy and includes landmasses some interpret as Antarctica's coastline free of ice. Most historians attribute these shapes to distortions or imaginative geography, yet the map's annotations claim it was compiled from older sources. Whether those sources were medieval, classical, or imagined remains contested. Still, the idea that geographic knowledge can cascade through layers of copying echoes how myths preserve information across eras. Language itself evolves like rock under pressure. Words shift meaning, compressing original references into metaphor. A world tree might encode an axis mundi, a concept linking sky, earth, and underworld, or perhaps a memory of a once central landmark. Flood myths may refer not only to water, but to any overwhelming transformation. Decoding such layers requires caution. Symbols can be multivalent. Yet dismissing them entirely risks overlooking human memory's creative resilience. If an intelligent species existed in deep prehistory, its cultural legacy would not survive as libraries but as fragments absorbed into later minds. Survivors of catastrophe might pass down cautionary tales, descriptions of lost homelands, or reverence for certain places. Over immense spans, those memories would detach from original context, merging with spiritual frameworks. The result would look like mythology, precisely what we have. Psychologists note that trauma imprints strongly on collective identity. Stories of destruction, exile, and renewal shape moral codes and cosmologies. If ancient disasters, natural or otherwise, affected early societies, their echoes would reverberate through ritual and narrative. Even without a prior high civilization, myth records environmental upheaval. The question remains whether some myths reach further back than accepted timelines. Interpreting myth as data demands interdisciplinary care, blending anthropology, linguistics, geology, and astronomy. No single story proves deep antiquity, yet patterns across cultures invite reflection. Myths may function like fossils of memory, incomplete, reshaped, but hinting at organisms of thought that once lived in different conditions. Whether those organisms represent purely symbolic constructs or distant recollections of lost knowledge remains open. But in the absence of stone walls, stories stand as another kind of ruin, intangible yet enduring, shaped by time, preserving traces of worlds that may have existed long before written history began. Intelligence does not appear fully formed. It emerges from pressures, opportunities, and accidents woven together over vast spans. On Pangaea, environmental conditions differed so radically from today that evolutionary pathways could have explored mental architectures unfamiliar to us. Oxygen-rich atmospheres in certain periods allowed larger body sizes and potentially higher metabolic rates, meaning more energy available for complex neural tissue. Brains are expensive organs, consuming disproportionate resources. Only when ecosystems provide surplus energy does cognition scale upward. Dense forests, rich coastlines, and interconnected habitats along Pangaea's margins could have offered such surpluses, we often imagine intelligence as tied to hands, upright posture, and vocal language because those traits define humans. Yet octopuses demonstrate problem-solving and tool use without bones or long lifespans, while birds like corvids fashion hooks from twigs. Neural complexity arises where selection rewards flexible behavior. In the late Paleozoic and early Mesozoic eras, synapsids, our distant evolutionary relatives, already showed differentiated teeth and more advanced jaw musculature, signs of increasing metabolic sophistication. Some lineages had enlarged temporal openings in the skull, allowing bigger jaw muscles but also accommodating brain growth. If one branch developed heightened sociality and communication, intelligence might have followed. Climate instability can accelerate innovation. Fluctuating conditions favor organisms capable of learning rather than relying solely on instinct. Seasonal shifts, drought cycles, and habitat fragmentation across Pangaea's interior deserts and coastal wetlands would pressure species to adapt behaviorally. Social groups that shared information about water sources or migration routes would gain survival advantages. From shared signals to symbolic communication is a long path, but evolution has time measured in millions of years, not generations. Tool use leaves minimal fossil traces unless tools are stone. Yet stone is only one option. Bone, wood, shell, and plant fibers can serve as implements but decay rapidly. If a species developed technology based on organic composites or bioengineered materials, grown rather than forged, its material culture might vanish entirely. Consider modern experiments in mycelium-based building materials grown from fungi into rigid forms. Such structures biodegrade, leaving little beyond altered soil chemistry. A civilization built on living materials would blend back into ecosystems almost seamlessly over geological timescales. Energy use defines technological ceilings. Fire represents a threshold, enabling cooking, metallurgy, and landscape modification. Evidence of ancient wildfires appears as charcoal in sediment layers. Distinguishing natural lightning fires from controlled burns would be challenging millions of years later. Patterns of repeated burning in specific zones, however, could signal intentional management. Today, humans shape ecosystems through agriculture and controlled fire, altering pollen records. Similar pollen anomalies in deep strata might reflect systematic environmental manipulation. Communication systems also shape civilization. Sound-based languages require atmospheric conditions supportive of vocal range. Denser air, as existed during high oxygen periods, carries sound differently, possibly affecting the evolution of calls and hearing. Visual signaling, color displays, bioluminescence, or patterned skin changes might serve communication in other taxa. Technology could evolve around these modalities, perhaps involving light-reflective materials or chemical signaling rather than written scripts. Without durable writing surfaces, records would depend on memory and ritual, increasing vulnerability to loss. Urbanization depends on resource concentration. Coastal estuaries rich in nutrients attract biodiversity and, by extension, intelligent predators or gatherers. Such areas also face flooding risk. On Pangaea, long uninterrupted coastlines might have hosted dense population corridors. Sea level fluctuations tied to glaciation and tectonics would periodically displace these groups, encouraging mobility and knowledge exchange across vast distances. Continuous land bridges eliminate maritime barriers, allowing rapid diffusion of ideas and genes. Conflict and cooperation drive technological change. Predation pressures, competition for resources, and social hierarchies select for planning and deception, cognitive traits underlying strategy. Archaeological signs of conflict in our own species include fortifications and weapon injuries. In deep time, such evidence would erode, but skeletal trauma patterns in fossil assemblages could hint at organized aggression. Interpreting such patterns would require careful differentiation from natural predation. Longevity influences cultural accumulation. Species with longer lifespans can transmit knowledge across extended periods, reducing loss. Some reptiles and marine animals exhibit longevity exceeding humans. If an intelligent lineage possessed similar traits, generational turnover would slow, allowing gradual cultural layering. Conversely, rapid reproduction with shorter lives could produce swift innovation, but also rapid forgetting. Evolution might balance these factors differently than in primates. Extinction filters possibilities. The end Permian and end Triassic events reset ecosystems, wiping out dominant groups and opening niches. Any intelligent lineage caught in such bottlenecks would face survival crises. A small remnant population might persist, losing complexity under stress, regressing to simpler survival strategies. Cultural collapse leaves few traces. Even today, knowledge loss occurs when societies fragment. Over millions of years, cycles of rise and fall could repeat without leaving continuous records. Ultimately, imagining intelligence on Pangaea means decentering human form. Minds might have arisen in bodies scaled, shaped, and sensed differently, perhaps amphibious, perhaps adapted to low-light forests, perhaps perceiving electromagnetic cues we ignore. Their technologies might exploit properties of materials we overlook. From our perspective, their artifacts could resemble natural formations, because our definitions of tools and structures are human-centric. Recognizing alien intelligence in Earth's own past requires expanding criteria beyond symmetry and stone to subtler signs of organized energy use and ecological engineering. Evolution's canvas is broad, and time supplies more paint than we can easily picture. Time does not flow evenly across history. It pools, accelerates, and collapses like a river, cutting through shifting ground. There are moments in Earth's past when change happened so quickly that ecosystems could not keep pace. These tipping points leave sharp lines in stone, abrupt boundaries where one world ends and another begins. If intelligence ever rose before our era, such boundaries would be the most likely places to search for its disappearance, not in ruins, but in global disruptions that echo the consequences of large-scale activity. The end Permian extinction stands as the most dramatic of these transitions. Volcanic outpourings in Siberia released vast amounts of carbon dioxide and methane, triggering greenhouse warming, ocean acidification, and oxygen loss in marine waters. Layers of rock from this time contain black shales, sediments rich in organic matter deposited under low oxygen conditions. Such anoxic events suffocate marine life and disrupt food chains. Yet the geochemical signals, rapid carbon isotope shifts and sudden metal enrichments, resemble effects that industrial processes could generate. The similarity does not equate cause, but it highlights how natural catastrophes and technological impact might converge in the geological record. Feedback loops amplify crises. Warming oceans release methane from hydrates, ice-like structures trapping gas under seafloor pressure. Methane, a potent greenhouse gas, accelerates warming further, a runaway effect. Today, scientists monitor these hydrates with concern. If an earlier civilization altered atmospheric chemistry, it might inadvertently trigger such loops, magnifying its footprint beyond initial actions. The resulting cascade could resemble volcanic or extraterrestrial events in scale. Sedimentary records also capture soot layers, tiny carbon particles from widespread burning. Large asteroid impacts can ignite global fires, but so can sustained biomass burning. Distinguishing between the two involves examining particle size and distribution. Impact-generated soot often pairs with shocked quartz, minerals deformed by extreme pressure, whereas controlled burning patterns might lack such markers. If anomalous soot layers appear without clear impact evidence, interpretation grows complex. Ocean circulation changes mark another boundary. During certain periods, evidence suggests that deep currents slowed or shifted, redistributing heat and nutrients. Such alterations affect climate globally. Modern humans influence circulation through warming and freshwater input from melting ice. A technologically active species could, intentionally or not, affect similar systems through coastal engineering or resource extraction, altering sediment flow into oceans. Layers rich in unusual mineral mixtures might result. Mass extinctions also reshape biodiversity patterns. After crises, opportunistic species diversify rapidly, filling emptied niches. The fossil record shows bursts of new forms after the Permian and Cretaceous events. If a civilization collapsed, its domesticates or associated species might survive and spread, leaving unexpected evolutionary signatures. Humans, for example, have transported rats and crops worldwide, altering ecological distributions. Detecting such patterns millions of years later would be subtle, but not impossible. Atmospheric changes leave traces in ice cores for recent epochs, and in mineral compositions for older ones. Sulfate aerosols from volcanic eruptions settle into layers. Industrial sulfur emissions do the same. Ancient evaporite deposits, minerals formed as water bodies evaporate, reflect climate shifts. A sudden spike in certain compounds might hint at large-scale processing of ores or fuels, though volcanic analogues exist. The scale of energy use distinguishes civilizations. A society harnessing planetary energy, comparable to what physicist Nikolai Kardashev called a Type 1 civilization, would manipulate climate, geology, and ecosystems. Signs of such manipulation could appear as synchronized global anomalies, simultaneous chemical shifts, extinction pulses, and sediment changes. Natural explanations remain strong, yet recognizing artificial amplification requires examining patterns holistically rather than in isolation. Another angle lies in the duration of anomalies. Volcanic episodes span hundreds of thousands of years. Asteroid impacts are brief but intense. Technological influence might produce sustained yet fluctuating signals over longer intervals, reflecting growth and decline. Layered sediment sequences could show repeated disturbances before stabilization, a rhythm unlike single-event catastrophes. Ultimately, tipping points illustrate vulnerability. Even advanced systems can unravel under compounded stress. The geological record demonstrates that Earth's biosphere has been pushed to near collapse multiple times. Whether these were purely natural or occasionally augmented by life's own experiments in complexity remains uncertain. What is clear is that the planet responds to perturbation with feedbacks powerful enough to reshape evolution itself. If intelligence once stood at such a precipice, its fall would not appear as toppled towers but as a line of darkness in stone, marking the moment when one trajectory of life ended and another began. Mathematics is not a human invention. It is a description of patterns that exist whether anyone observes them or not. Circles form under surface tension, spirals emerge in galaxies and shells, ratios repeat in leaf arrangements because growth follows efficiency. Any intelligence studying its surroundings would eventually uncover these regularities. That universality creates an intriguing possibility. If a prior civilization existed, traces of its thinking might survive not as language, but as geometry embedded in the environment. Certain mathematical relationships appear frequently in nature because they optimize energy and space. The Fibonacci sequence, where each number is the sum of the two before it, produces spirals that pack seeds efficiently in a sunflower head. The golden ratio, approximately 1.618, arises in growth processes where proportional scaling is beneficial. If intelligent beings engineered structures or landscapes using such principles, their designs might harmonize so well with natural forms that they evade detection, appearing organic rather than constructed. Astronomy offers another universal framework. Orbital mechanics obey gravity's equations everywhere. The spacing of planets in a system often follows rough patterns due to resonances, gravitational interactions that lock bodies into stable relationships. Humans once proposed the Titius-Bode law to describe planetary distances, a numerical pattern that seemed predictive. While not exact, it hinted that cosmic order can be expressed mathematically. An advanced civilization might encode knowledge in astronomical alignments using star positions as reference markers. Such alignments could endure if carved into bedrock or expressed in large-scale landscape modification. On Earth, large structures aligned with solstices or equinoxes demonstrate how observation of celestial cycles informs architecture. Over deep time, tectonics would distort such alignments, yet some relationships might persist regionally. A pattern of ancient quarries or earthworks aligned to stellar events could, after erosion, resemble natural ridges unless measured precisely. Recognizing intention would require statistical analysis, separating chance alignment from deliberate orientation. Prime numbers, integers divisible only by 1 in themselves, are another mathematical constant. They form the basis of cryptography because of their properties in factorization. Some scientists have suggested that prime sequences could serve as universal signals recognizable by any intelligence. If a civilization sought to leave a message resilient against decay, it might encode primes in arrangements of stones, landscape features, or even genetic sequences of domesticated species. Detecting such encoding would challenge assumptions about randomness in natural distributions. Crystal structures illustrate how order arises spontaneously. Atoms arrange in repeating lattices, forming minerals with precise angles. Humans exploit this regularity in technology, from silicon chips to lasers. A deep-time society might have manipulated crystalline growth, creating materials with tailored properties. Over millions of years, distinguishing engineered crystals from rare natural forms would require microscopic and isotopic scrutiny. Geometry also governs erosion. Rivers carve branching networks following fractal patterns, self-similar shapes repeating at different scales. If large-scale earthworks mirrored or modified such networks, differentiating natural from artificial could be subtle. Consider modern examples of terracing or irrigation canals visible from satellites. After geological time, These might appear as unusual sedimentary features unless context survived. Physics imposes further constraints. Energy transfer, thermodynamics, and material limits apply universally. Efficient structures minimize stress, often resulting in curved forms like arches or domes. Nature uses similar shapes in shells and bones. A civilization optimizing for strength and economy might converge on these geometries, blending artifact with organism-like appearance. Information theory adds another dimension. Entropy measures disorder. Living systems maintain low entropy locally by exporting disorder elsewhere. Technology accelerates this process, increasing global entropy through energy use. In the geological record, entropy manifests as mixing of materials and altered chemical gradients. A civilization's long-term footprint might be a spike in entropy production detectable as widespread geochemical anomalies. Time complicates perception of order. Plate tectonics shifts coordinates. Stars drift across the sky due to proper motion. Alignments meaningful millions of years ago may no longer correspond to current positions. Decoding such ancient signals would require reconstructing past celestial configurations, a task astronomy can attempt through modeling. Ultimately, mathematics bridges mind and matter. It offers a language independent of biology, capable of persisting through transformation. If intelligence once shaped Earth, its most durable legacy might not be monuments, but patterns, subtle regularities in orientation, distribution, or proportion that deviate from expected randomness. Recognizing them demands openness to the idea that design can hide within nature's own grammar, indistinguishable at first glance, yet whispering of thought long dissolved into the fabric of the planet. Energy is the true currency of civilization. Tools, language, and culture matter, but what ultimately defines a society's reach is how much energy it can control and how efficiently it can use it. On a planet-scale timeline, shifts in energy use leave broader traces than buildings or artifacts. Fire alters carbon cycles, metallurgy redistributes elements, and large-scale engineering reshapes landscapes. If an advanced civilization existed on Pangaea, its relationship with energy would have determined both its power and its vulnerability. Biological life runs on solar energy captured through photosynthesis, stored in chemical bonds. Coal deposits formed in the Carboniferous period when vast swamp forests buried plant matter faster than it could decay, locking carbon underground. These deposits later became the fuels that launched human industry. A prior civilization might have accessed similar stores, or even earlier ones now deeply buried. Large-scale combustion of such fuels would shift atmospheric carbon isotopes, favoring lighter carbon-12, just as modern fossil fuel burning does. In rock layers, this appears as a sudden negative carbon isotope excursion, a drop in the ratio of carbon-13 to carbon-12. Metallurgy represents another energy-intensive leap. Extracting metals from ore requires high temperatures, often achieved through charcoal or other fuels. Smelting leaves slag, ash, and altered mineral residues. Even if slag eroded, local concentrations of metals like copper, tin, or rare earth elements might persist in unusual ratios. Hydrothermal systems naturally concentrate metals, but patterned depletion, areas where certain ores are unexpectedly exhausted, could hint at extraction. Heat itself leaves marks. Sustained industrial heat release might affect microclimates, altering vegetation patterns and soil formation. On human timescales, urban heat islands raise local temperatures. Over longer periods, widespread energy use could influence weathering rates and sediment transport. Enhanced erosion near population centers might deposit thicker sediment layers downstream, creating subtle stratigraphic signals. Radiation provides a different signature. Nuclear reactions, whether natural or artificial, produce isotopes not commonly found otherwise. On Earth, natural nuclear fission occurred 2 billion years ago in the Oklo region of Gabon, where uranium deposits reached criticality. The isotopic evidence remains detectable. A technological civilization using nuclear processes might leave similar isotopic anomalies, unusual ratios of xenon or neodymium isotopes, for example. Such markers would endure longer than physical structures. Renewable energy use might be less visible. Wind, water, and geothermal sources leave minimal residue. However, large-scale hydrological engineering, dams, canals, reservoirs, reshapes sedimentation. Dams trap sediments, starving downstream deltas. In geological layers, sudden changes in sediment grain size or composition could reflect upstream control of rivers. Over millions of years, these features blur but may still appear as unusual depositional patterns. Waste is another energy byproduct. Industrial societies generate materials difficult to recycle biologically, from plastics to synthetic chemicals. While many degrade, some molecular fragments could remain as persistent organic pollutants detectable in sediments. Even altered ratios of nitrogen and phosphorus from agriculture affect ecosystems, producing eutrophication, oxygen-depleted waters. Black shales rich in organic matter sometimes form under such conditions, though natural upwelling can produce similar effects. Energy infrastructure also influences magnetism. Large electrical currents create magnetic fields. While modern grids operate on regional scales, a global network might generate measurable disturbances. Minerals forming during such periods could record slight anomalies in magnetic orientation. Separating this from natural geomagnetic variation would be extremely challenging but conceptually possible. Scale matters most. A small, scattered culture leaves faint traces. A planetary civilization, however, alters global cycles. The Anthropocene concept recognizes this for humanity. We have become a geological force. Similar recognition could apply retroactively if evidence surfaced for past global disruptions tied to biological agency rather than purely geophysical events. Yet energy dependence also invites collapse. Resource depletion, climate feedbacks, and environmental degradation can undermine the very systems that sustain complexity. A civilization drawing heavily on fossil carbon might trigger warming, ocean acidification, and ecosystem collapse, parallels to end Permian conditions. If such a society lacked resilience or foresight, its downfall could coincide with a mass extinction, its footprint blending into the broader catastrophe. Energy transitions may leave layered records. Initial expansion produces one set of anomalies. Decline produces another. Abandoned infrastructure decays, releasing stored materials. Fires from neglected systems might spike soot deposition. Population reduction decreases environmental pressure, allowing recovery. Such oscillations might appear as repeated pulses in sedimentary and geochemical data. Ultimately, energy links mind to planet. Intelligence channels energy flows in novel ways, accelerating processes that would otherwise proceed slowly. These accelerations are the footprints most likely to endure. Stone crumbles, metal rusts, but altered elemental cycles and isotopic ratios persist as signatures written into Earth's metabolism. Reading those signatures requires viewing geology not only as a record of volcanoes and impacts, but as a ledger of life's experiments with power. Whether any entry in that ledger predates humanity remains uncertain, yet the principle stands: follow the energy, and you follow the possibility of intelligence etched into the deep past. Continents are not fixed backdrops, but travelers drifting atop semi-molten mantle in a process called plate tectonics, where rigid crustal plates move centimeters per year, collide, split and slide past one another. Over tens of millions of years, this motion rearranges oceans and land like pieces on a slow, inexorable chessboard. Any surface trace of deep antiquity must survive this restlessness. Most do not. Yet fragments of old crust called cratons act like anchors, thick, buoyant blocks that resist subduction and preserve rock billions of years old. If any physical remnants of extreme antiquity endure, they would most likely reside on these stable cores. Cratons such as those in parts of Africa, Canada, and Australia contain ancient shields, exposed rock platforms bearing scars from vanished mountain ranges and seas. These regions have experienced erosion, burial, and uplift repeatedly, but they have avoided the recycling that erases oceanic crust. Sedimentary basins on craton margins accumulate layers like stacked pages, each recording environmental shifts. Within such basins, anomalies, unusual mineral concentrations, abrupt chemical changes, or unexplained structures would stand out against otherwise gradual geological narratives. Mountain building events, or orogenies, also reshape crust. When plates collide, sediments and crustal fragments are thrust upward, forming ranges like the Himalayas. During these events, older rocks may be pushed over younger ones along thrust faults, complicating age interpretation. Objects trapped in such processes could be transported far from their origin. A hypothetical artifact buried in sediments might later appear high in a mountain belt, its context scrambled. Geologists untangle such puzzles using radiometric dating, measuring decay of isotopes like uranium to lead to determine rock ages independent of position. Heat and pressure alter rocks through metamorphism, transforming shale into slate or limestone into marble. These processes recrystallize minerals, potentially erasing original textures. Yet some inclusions survive, like time capsules within crystals. Tiny zircon grains, for example, can preserve isotopic signatures from the early Earth. If materials created by intelligence were incorporated into sediments and later metamorphosed, microscopic residues or unusual isotopic ratios might persist in such resistant minerals. Subduction zones where one plate dives beneath another act as geological shredders. Sediments and crust descend into the mantle, melting and mixing. However, some fragments escape, scraped off and added to the overriding plate. These accreted terrains form patchwork regions with complex histories. Studying them reveals unexpected fossils and rock types far from their origin. Such geological mosaics could, in theory, harbor traces transported from distant environments, though context would be obscure. Rifting, the process of continents pulling apart, creates basins that fill with sediments and volcanic rocks. These rift basins sometimes preserve footprints, plants, and even raindrop impressions. Fine-grained sediments deposited in quiet water capture detail exquisitely. If surfaces bearing signs of structured activity were buried quickly in such settings, they might fossilize. Later, erosion could expose them millions of years afterward, though distinguishing natural from artificial patterns would challenge interpretation. Erosion both destroys and reveals. Wind, water, and ice wear down mountains, carrying sediments to seas. Over time, erosion can expose deep layers once buried. Human archaeology relies on such exposure. In deep time, however, erosion may strip away entire sedimentary sequences, leaving gaps called unconformities, intervals where time passed without record. These gaps are blind spots. Any traces from those periods would be lost. Mineral deposits sometimes form in patterns influenced by structural controls like faults and fractures. Mining today leaves voids and altered zones. Over geological spans, collapse and infill would obscure these features. Yet unusual geochemical halos, zones of altered mineral composition, could linger. Distinguishing natural hydrothermal alteration from extraction signatures would require subtle analysis of isotopes and trace elements. Tectonic motion also affects climate. Continental positions influence ocean currents and atmospheric circulation. When Pangaea existed, its interior dryness contrasted with humid coasts. As it broke apart, new seaways changed heat distribution, impacting life's evolution. An intelligent species adapting to such shifts might migrate along emerging coastlines, leaving a moving footprint. Geological records would show cultural centers appearing in different regions sequentially, though without context, they might resemble separate natural phenomena. Ultimately, tectonics teaches humility. The planet's surface is temporary, constantly rewritten. What seems permanent on human scales dissolves over millions of years. Searching for deep-time intelligence means reading a palimpsest where older text has been scraped and overwritten by younger geology. Yet cratons, basins, and microscopic mineral archives offer rare windows into remote epochs. Within these windows, anomalies might whisper of processes beyond volcanism and sedimentation, subtle hints that the Earth's restless crust once carried not only mountains and seas, but perhaps minds whose works now lie folded into stone. Extinction is not just disappearance, it is a reset switch in the operating system of life. When dominant species vanish, ecological space opens like cleared land after a wildfire, inviting new forms to experiment. The fossil record shows this pattern repeatedly, long stretches of relative stability punctuated by sharp collapses followed by bursts of innovation. These pulses are usually framed as nature's own rhythms, volcanism, asteroid impacts, climate swings, but they also define the windows in which complex societies, if they existed, would have either flourished or failed. The end Triassic extinction about 201 million years ago marks one such turning point. It coincided with the breakup of Pangaea and massive volcanism that flooded the atmosphere with carbon dioxide. Temperatures rose, oceans acidified, and many species disappeared, clearing the stage for dinosaurs to dominate. The pattern of loss was selective. Some groups vanished while close relatives survived. Selectivity can arise naturally from physiological tolerances, yet in modern extinctions, human activity also produces uneven impacts. Species tied to particular habitats or food webs suffer first. In stone, selective extinction can look like a puzzle with missing pieces. Fossil assemblages sometimes contain Lazarus taxa, species that vanish from the record for millions of years and then reappear. Gaps in preservation explain some cases, but others raise questions about refugia, isolated environments where life persists while elsewhere it declines. If an intelligent lineage faced global catastrophe, refugia would be crucial. Deep valleys, cave systems, or sheltered coastlines might harbor remnant populations. Over time, such survivors could lose complexity, adapting to survival rather than innovation. Their technological past would fade, leaving only biological continuity. Bone chemistry reveals stress. Ratios of certain isotopes in fossilized teeth and shells indicate changes in diet, temperature, or water composition. Sudden shifts suggest environmental upheaval. If a civilization altered landscapes through agriculture, deforestation, or resource extraction, local ecosystems would change. Animals feeding in those systems would record the disturbance in their tissues. Layered across regions, such shifts might form a mosaic of ecological pressure preceding broader extinction. Another clue lies in bioturbation, the mixing of sediments by organisms like worms or burrowing animals. In stable environments, bioturbation blurs sediment layers. After mass die-offs, reduced activity leaves clearer laminations, thin, undisturbed layers. Some extinction boundaries show this effect. A sudden drop in bioturbation could result from oxygen loss or toxicity, but widespread pollution might produce similar conditions. Again, natural and artificial causes can converge in outcome. Evolutionary bottlenecks shrink genetic diversity. Though DNA rarely survives millions of years, indirect evidence comes from morphological uniformity in fossils, populations looking more alike than before. Bottlenecks follow catastrophes, but could also follow technological collapse if societies dependent on complex systems faltered, reducing population sizes drastically. Over geological spans, such demographic shifts would blur, yet patterns of reduced diversity followed by radiation might echo cycles of rise and fall. Behavior leaves faint marks. Nesting sites, trackways, and burrows occasionally fossilize. Repeated patterns of modification, arranged stones, structured burrow complexes, might hint at organized activity. However, many animals build intricate structures. Termites create mounds with ventilation systems rivaling human engineering in efficiency. Distinguishing biological architecture from cultural construction would demand criteria beyond complexity alone. Plants also respond to disturbance. Pollen records in sediments chart vegetation changes. Rapid shifts from forest pollen to grasses or pioneer species indicate disruption. Modern deforestation produces such signals. In deep time, volcanic ash or climate change can do the same. Still, regional synchronicity of unusual vegetation transitions might suggest coordinated landscape alteration. Mass extinction horizons often feature disaster taxa, opportunistic organisms thriving in stressed environments like certain ferns that colonize burned areas. A global fern spike appears after the asteroid impact that ended the dinosaurs. Similar spikes might follow other disruptions. If technological collapse triggered widespread fires or habitat change, comparable patterns could appear. The broader perspective reveals a planet accustomed to turnover. Dominance is temporary. Species that seem invincible, trilobites in the Paleozoic seas, dinosaurs in the Mesozoic, vanished, leaving only traces. If intelligence arose earlier, it too would have faced the same fragility. Geological records of extinction do not name the lost, but they chronicle conditions under which complexity faltered. Reading these layers is like examining the aftermath of a vanished city without ruins, only ash, altered soils, and changed wildlife. Causes blur together. Natural disasters and self-inflicted crises might produce indistinguishable signatures. Yet the repeated theme is vulnerability. When systems grow intricate, They also grow sensitive. Whether driven by magma beneath or mined above, tipping points can erase epochs, leaving only transitions etched in fossil and stone, silent witnesses to possibilities that once unfolded on a living, changing Earth. Deep beneath mountains and plains, the mantle moves in slow convection, currents of hot rock rising and cooling rock sinking, a circulation that takes tens of millions of years to complete a cycle. This motion is invisible to the eye, yet it drives plate tectonics, volcanoes, and the magnetic field that shields life from solar radiation. Any intelligence reaching advanced levels would eventually confront these planetary systems, not as abstract forces, but as constraints and opportunities. Understanding Earth's interior means understanding the engine that reshapes the surface on which civilization stands. Volcanism provides both destruction and creation. Lava builds new land, but eruptions also release gases, carbon dioxide, sulfur dioxide, water vapor, that influence climate. Large igneous provinces, vast outpourings of basalt, coincide with some mass extinctions. The Siberian traps and Deccan traps cover regions the size of continents. Their layered flows resemble giant geological staircases. If an advanced species sought geothermal energy tapping magma heat, it might concentrate activity near volcanic zones. Such exploitation could alter local hydrothermal systems, changing mineral deposition patterns in ways subtle but detectable. Hydrothermal vents on the ocean floor demonstrate how life thrives on geothermal energy alone. These vents deposit metals in chimney-like structures, forming ore bodies. Mining such environments would disturb vent ecosystems and redistribute metals. Over time, sediment layers could record unusual depletion or redistribution zones around vent fields. Distinguishing these from natural hydrothermal variation would require mapping patterns at regional scales. The magnetic field originates in Earth's liquid outer core, where convecting iron generates electrical currents, a geodynamo. Magnetic reversals, where north and south poles swap, occur irregularly. Rocks preserve these flips in magnetic minerals. Long intervals without reversals, called supercrons, indicate unusual core stability. If surface processes, such as large-scale energy grids or electromagnetic manipulation, influence the magnetosphere, tiny anomalies might appear in rock records. While speculative, the concept illustrates how deeply technology might interact with planetary systems. Earthquakes mark stress release along faults. Modern monitoring shows that human activities, reservoir filling, mining, fluid injection, can trigger quakes. A large-scale civilization altering crustal loads could influence seismicity. Patterns of induced seismic events might leave traces in sedimentary layers as turbidites, underwater landslides triggered by shaking. Repeated turbidite sequences without clear tectonic drivers could raise questions, though natural variability remains strong. Mantle plumes, columns of hot rock rising from deep within Earth, create volcanic chains like Hawaii. These hotspots drift relative to plates, leaving tracks of islands. If a civilization used volcanic islands strategically, for energy or resource extraction, its footprint might migrate with plate motion, appearing as sequential disturbances along a plume track. Sedimentary anomalies in these regions could mark repeated habitation or exploitation. Atmospheric shielding from solar radiation depends on both the magnetic field and ozone. Large-scale emissions of certain gases can deplete ozone, increasing ultraviolet radiation. Geological evidence of increased UV exposure appears as mutations in fossil pollen or spores. Such signals are known from periods of volcanic outgassing. Technological emissions might produce similar effects, leaving biological stress markers. Water cycles also connect surface and interior. Subduction carries water into the mantle, influencing melting and volcanism. Surface engineering, massive reservoirs or redirection of rivers, alters erosion and sediment transport, indirectly affecting subduction inputs. Over geological time, such changes could influence arc volcanism chemistry, perhaps detectable in trace element ratios. Life itself modifies planetary systems. Photosynthetic organisms oxygenated the atmosphere billions of years ago, transforming climate and geology. This great oxidation event left a signature in banded iron formations, layers of iron oxides precipitated as oxygen rose. It demonstrates that biology can produce planetary-scale change. A technological biosphere could represent another such transformation, though likely briefer. The interplay between surface life and deep Earth processes forms a feedback loop. Climate influences erosion. Erosion affects sedimentation. Sedimentation alters crustal stress and subduction. Subduction feeds volcanism. Volcanism returns gases to the atmosphere. An intelligent species inserting itself into this loop would amplify certain pathways, accelerating change. Geological records of abrupt shifts in multiple systems simultaneously might reflect such amplification. Yet the mantle's timescale dwarfs cultural spans. Civilizations rise and fall in thousands of years. Mantle cycles take millions. Even a long-lived species would be a flicker compared to convection. Its influence, unless immense, would register as a thin layer in rock, a brief perturbation in a vast system. Still, the fact that life has already altered planetary chemistry once suggests that further alterations are possible. The boundary between natural and artificial blurs when life itself becomes a geological force. In deep strata, evidence of altered volcanic chemistry, unusual seismic patterns, or biological stress could hint at interactions between mind and mantle. Whether such interactions ever occurred before humanity remains unknown, but the framework exists, a living planet whose interior and surface constantly converse, and where intelligence, if present, becomes another voice in that conversation, briefly loud, then fading into the slow rumble of stone. Technology does not have to look like metal towers and straight roads. It is a method, not a style, a way of shaping matter and energy toward intention. Human expectations bias the search for past intelligence because we imagine machines in familiar forms. Yet evolution and environment could drive a different aesthetic entirely, one where living tissue, chemistry and geology blend so seamlessly that artifacts appear organic. On Pangaea, with climates and ecosystems unlike today's, technological solutions might have grown rather than been built. Biological engineering offers one model. Even now, humans cultivate materials from organisms. Bacteria produce plastics, fungi grow structural composites, and coral can be guided to form building frameworks. Such materials self-repair and biodegrade, merging with surrounding ecosystems after abandonment. Over millions of years, distinguishing an engineered fungal lattice from a natural one would be nearly impossible. Residual clues might lie in isotopic ratios or unusual symmetries in growth patterns, but the line between natural and artificial would blur. Chemical technology provides another path. Organisms already synthesize complex compounds for defense, signaling, and structure. An intelligent lineage might refine these pathways, producing polymers or crystalline structures optimized for function. These could resemble rare minerals or resins. Once buried and altered, their origins might be misread as unusual geochemistry rather than manufacturing. Sound and vibration might serve as tools. Certain frequencies can fracture stone or influence crystallization. Natural examples include sonic weathering by waves or vibrations during earthquakes. A species attuned to acoustics might develop construction methods based on resonance, shaping landscapes through controlled vibration. Geological records might show unusual fracture patterns or alignments difficult to explain solely by tectonics. Light-based technology also leaves subtle traces. Laser-like effects occur naturally in some crystals, but organized photonic systems, using light for energy transfer or communication, could involve arrangements of reflective minerals. After weathering, such systems might leave only altered crystal orientations or localized melting. Agricultural engineering would reshape biospheres. Selective breeding and genetic manipulation alter species rapidly. Fossil pollen records already reveal shifts when humans clear forests. A deep-time civilization cultivating specific plants might leave monoculture pollen signatures or abrupt introductions of species outside expected ranges. Over millions of years, evolutionary drift would obscure domestication traits, but sudden morphological changes in plant lineages might hint at intervention. Waste recycling in a biologically integrated society might minimize persistent residues. Nutrient loops could be closed with byproducts reabsorbed into ecosystems. In such a case, technological activity would leave fewer chemical scars than modern industry. The civilization's footprint would resemble intensified ecological engineering rather than industrial pollution. Architecture might integrate with geology. Structures carved into cliffs or grown from mineral accretion could mimic natural formations. Stromatolites, layered microbial mounds, already form dome-like shapes. Artificial analogues might use similar layering techniques. Over time, distinguishing constructed layers from sedimentary deposition would challenge interpretation. Energy systems based on gradients, thermal, chemical, or electromagnetic, might require no combustion. Geothermal vents, tidal flows, or atmospheric electricity could power societies with minimal atmospheric alteration. Such technologies would leave faint traces, perhaps limited to localized mineral changes near energy capture sites. Communication networks might exploit biological signals like pheromones or electrical impulses in conductive organisms. These systems would decay with the organisms themselves, leaving no durable infrastructure. Cultural memory might reside in behavior rather than objects, disappearing with extinction. Transportation could follow natural corridors, rivers, coastlines, migratory routes, without roads. Movement patterns might shape animal distributions or sediment pathways indirectly. Archaeological visibility would be low. Aesthetic preferences influence material choices. If a species valued camouflage or ecological harmony, it might deliberately avoid imposing geometric forms. Its cities could resemble forests or reefs optimized for function but visually indistinct from nature. Erosion would complete the disguise. Recognizing such a civilization in the geological record demands looking beyond traditional artifacts. Patterns of coordinated ecological change, synchronized chemical anomalies, or structures exhibiting statistical regularity beyond natural expectation might be the only clues. The absence of obvious ruins does not preclude sophistication. It may indicate a technology aligned with life's cycles rather than opposed to them. This possibility reframes the search. Instead of expecting alien skyscrapers fossilized in stone, one might expect whispers, subtle reorganizations of matter and life that signal intention without monumentality. Deep time would erase the living surfaces, but underlying patterns could remain, faint signatures of minds that once shaped their world through growth, chemistry, and resonance, then vanished so thoroughly that their works merged back into the planet's own architecture. Time on a planetary scale does not resemble a straight line, but a series of overlapping waves, each cresting and breaking in its own rhythm. Civilizations, if they arise, would ride these waves the way reefs grow along shifting shorelines, sometimes flourishing in calm, sometimes shattered by forces beyond their control. Geological cycles provide the tempo, ice ages advancing and retreating, sea levels rising and falling, continents assembling and fragmenting. Against this backdrop, intelligence would not be a permanent ruler but a temporary pattern, emerging where conditions align and dissolving when they shift. Orbital mechanics drive some of these cycles. Variations in Earth's orbit, its tilt, wobble, and the shape of its path around the Sun alter how sunlight distributes across the planet. These Milankovitch cycles, spanning tens to hundreds of thousands of years, trigger glacial and interglacial periods. Ice sheets expand, locking water on land and lowering sea levels, then they melt, flooding coasts. For coastal societies, these changes redraw maps repeatedly. Settlements become seabeds, and seabeds become plains. Over millions of years, such oscillations erase surface continuity, ensuring that even long-lasting cultures must adapt or relocate. Superimposed on orbital cycles are tectonic rhythms. The supercontinent cycle assembles land into a single mass and later disperses it, roughly every 400 to 600 million years. Pangaea was one iteration. Earlier came Rodinia and Columbia. Each configuration alters ocean circulation and climate, influencing evolution. During assembly phases, interiors grow arid. During breakup, new coastlines bloom with biodiversity. If intelligence favors ecological richness and connectivity, it might peak during dispersal phases, then decline as continents merge again into harsher interiors. Solar evolution adds another layer. The Sun brightens gradually over geological time, increasing Earth's baseline temperature. Life adapts through feedbacks like carbon sequestration in rocks and oceans. An advanced species would need to manage these slow drifts, perhaps engineering climate or migrating habitats. Failure to do so could lead to decline, not from sudden catastrophe, but from incremental stress. Asteroid impacts punctuate the rhythm unpredictably. Most are small, but occasional large bodies reshape ecosystems globally. The Chicxulub impact 66 million years ago ended dinosaur dominance. Such events act as cosmic resets, independent of planetary processes. A civilization at its height might be extinguished in moments by an external blow. Geological records of impacts, shocked minerals, iridium layers, mark these abrupt interventions. Volcanism, driven by mantle dynamics, also cycles. Periods of heightened activity release gases and particulates, affecting climate. Flood basalt events correlate with mass extinctions. An intelligent species might attempt to mitigate or harness such forces, but large-scale eruptions operate beyond easy control. Cultural narratives of fire from the Earth could reflect encounters with these forces. Ecological succession mirrors geological cycles on smaller scales. After disturbance, pioneer species colonize, followed by more complex communities. Civilizations might mirror this pattern, rising in stable phases, fragmenting during stress, and re-emerging elsewhere. Over deep time, such cycles could repeat multiple times without leaving continuous traces. Feedback loops tie these rhythms together. Ice growth increases reflectivity, cooling climate further. Warming melts ice, lowering reflectivity. Vegetation influences carbon storage. Carbon affects temperature. Intelligent intervention could amplify or dampen these loops. Yet maintaining balance across interconnected systems is complex. Miscalculations might push systems toward tipping points. Cultural memory would struggle against such scales. Even if knowledge passed across generations, geological upheaval would sever continuity. Oral traditions might preserve echoes of earlier cycles, encoded as myths of worlds destroyed by ice, water, or fire. These stories would serve as warnings, though their original contexts fade. The concept of cyclic time appears in many philosophies, reflecting observation of natural repetition. If civilizations recur, each might rediscover knowledge, believing itself first. Artifacts from earlier cycles would be rare, scattered like driftwood from previous tides. From this perspective, humanity's era becomes one crest in a long sequence. Whether earlier crests carried other intelligences cannot be proven easily, but the framework allows for it. Planetary systems are dynamic, not static backdrops. They shape possibilities, enforce limits, and occasionally erase entire chapters. Recognizing this cyclicity shifts emphasis from permanence to process. Intelligence becomes a transient strategy within life's broader experiment, not an endpoint. The deep past may have hosted other experiments, now dissolved into sediment and memory. The rocks record cycles faithfully, whether they also hide the faint signatures of minds that once navigated those cycles remains a question written between the layers, waiting for eyes patient enough to read rhythms measured not in centuries, but in revolutions of continents and stars. Perspective changes everything. On the scale of a human life, mountains seem eternal, oceans fixed, and the ground beneath our feet solid beyond question. On the scale of geological time, those same mountains are ripples that rise and vanish, oceans open and close like breaths, and continents wander like slow herds across the mantle. When intelligence enters this picture, it is tempting to place it at the center, to imagine history converging toward awareness as its goal. Yet the deep record suggests something different. Intelligence may be an episode, not a destiny, one expression of life's capacity to organize matter temporarily against the drift toward disorder. The thermodynamic concept of entropy describes this drift. Systems tend naturally toward greater disorder, yet life locally reverses this trend by using energy to build structure. A forest is low entropy compared to scattered molecules. A city is lower still, concentrating order through design. But maintaining order requires continuous energy flow. When that flow falters, structures decay. On planetary timescales, even mountains erode and stars exhaust their fuel. Civilizations, as highly ordered systems, exist on borrowed time, sustained only while energy gradients remain accessible. This fragility reframes the search for deep time intelligence. Instead of asking where monuments are, the question becomes how long organized complexity can persist before dissolving. The answer may be shorter than intuition suggests. Human technological society spans mere centuries. Even if extended to millennia, it remains brief against tectonic or orbital cycles. A previous civilization lasting 1 million years, a staggering duration by our standards, would still leave only a thin geological trace. Yet order leaves patterns. Information theory defines information as a reduction of uncertainty. When matter arranges in highly specific configurations, machined surfaces, alloy compositions, structured networks, it embodies information. Over time, noise erodes information, but not uniformly. Some patterns survive as statistical anomalies. Detecting them requires comparing expectations of randomness with observed distributions. This approach underlies searches for extraterrestrial signals, looking for non-random radio patterns. The same logic could apply to geology, seeking material arrangements unlikely to arise through known natural processes. Philosophically, the possibility of prior intelligence challenges human exceptionalism. Many cultures have imagined cycles of creation and destruction, suggesting that earlier worlds existed before ours. Modern science recognizes extinction and evolution, but rarely entertains multiple technological epochs. Yet given life's 4-billion-year history, the window for intelligence seems wide. The rarity of evidence may reflect not absence but erasure. Psychology shapes interpretation. Humans excel at pattern recognition but also at confirmation bias, seeing what fits expectations. Scientists guard against this by demanding reproducibility and parsimonious explanations. Claims of deep-time civilizations would require extraordinary proof. Still, openness to possibility encourages refinement of methods. New technologies, high-resolution geochemical mapping, subsurface imaging, machine learning applied to pattern detection, expand our ability to see subtle signals. Ethically, contemplating earlier lost civilizations invites reflection on our own trajectory. If complexity has risen and fallen before, permanence is illusion. Awareness of fragility might encourage stewardship rather than exploitation. Geological humility, recognizing Earth's processes dwarf human timescales, tempers arrogance. From a cosmic perspective, intelligence anywhere is rare and precious, a brief flame in vast darkness. Whether that flame has flickered here more than once remains uncertain, but the rocks beneath us carry the cumulative memory of planetary change, including life's experiments. Each fossil, each isotopic ratio, each sediment layer is a sentence in a book still being translated. Perhaps the most important shift is from seeking certainty to embracing inquiry. The absence of clear evidence does not end the question, it defines its difficulty. Deep time is a filter, removing detail, preserving only essentials. If intelligence once walked Pangaea's coasts, its footsteps are gone, but its influence, if great enough, might persist as altered cycles, unusual distributions, or echoes in myth and math. Standing at this moment in Earth's history, with tools to probe atom and star, we become participants in the same process. Life-shaping matter, generating order, asking about its origins. Whether first or latest in a sequence, the act of questioning binds us to the planet's story. The possibility that others asked similar questions long ago adds depth to our place in that narrative, suggesting that intelligence, like continents, may rise, merge, fragment, and sink, leaving only faint signatures for future minds to ponder. Stone closes over everything in the end. Forests fall and turn to coal, oceans retreat and leave salt deserts, mountains rise and grind back into sand. The planet does not remember stories the way minds do, it remembers pressure, chemistry, and motion. Yet within those memories lie the faintest possibility that awareness has come and gone before, like tides leaving subtle lines on rock. The question of a civilization on Pangaea does not hinge on finding a city frozen in time, but on whether the planet's long memory contains patterns that cannot be fully explained by blind geology alone. Across the journey through deep time, one theme repeats. Processes overlap. Volcanism, climate cycles, orbital shifts, biological innovation, and extinction events weave together into a fabric so complex that cause and effect blur. Intelligence, if it emerges, would be another thread in that weave, not separate from nature, but an intensification of it. Minds channel energy, reorganize materials, and alter ecosystems, accelerating transformations already underway. The geological record shows many rapid changes, but rapid does not automatically mean artificial. Nature itself is capable of violence on unimaginable scales. Still, life has already demonstrated planetary impact. The rise of oxygen billions of years ago, driven by photosynthetic microbes, altered the atmosphere permanently. Banded iron formations, striped rocks formed as oxygen reacted with dissolved iron in ancient seas, remain as proof that biology can rewrite planetary chemistry. If simple cells could do that, more complex intelligence might leave equally profound marks, though perhaps briefer. The difficulty lies in recognition. Our tools and expectations are tuned to human patterns, straight lines, right angles, metals shaped by heat. But deep time erodes geometry first. What endures are shifts in ratios, anomalies in distributions, and scars in ecosystems. Reading those requires patience and imagination balanced with rigor. Every anomaly must first face natural explanation. Only when patterns resist known processes does the door open slightly to other possibilities. The silence of the record is not empty. It is dense with overlapping signals. Sediment layers capture climate, erosion, life, and catastrophe in compressed form. Like a palimpsest, a manuscript written over older text, Earth's crust carries traces of earlier chapters beneath newer ones. Some may be forever illegible, erased by heat and pressure. Others may still whisper through isotopes, microstructures, or unexpected alignments. The idea that intelligence might not be unique to our moment reshapes perspective. It suggests that awareness is not a singular miracle, but a recurring potential, surfacing when conditions align, fading when they shift. Each emergence would face the same constraints: energy limits, environmental feedbacks, cosmic hazards. Some might leave little trace, others might alter the planet briefly before vanishing. This possibility does not diminish the present, it deepens it. If minds have risen before, then consciousness is a pattern Earth can generate, not an accident isolated in time. If none came before, then the rarity of our moment is even more profound. Either way, the responsibility remains the same: to recognize fragility and interconnection. Looking outward, we search the stars for other intelligences, scanning radio waves for non-random signals. Yet beneath our feet lies an equally vast unknown, a deep archive of our own planet's past. The search inward and the search outward share a method, looking for order against the background of noise. In space, that noise is cosmic radiation. In stone, it is geological process. One day, new techniques may reveal patterns we cannot yet see. High-resolution elemental mapping, advanced simulations of deep-time environments, and interdisciplinary approaches could sharpen interpretation. Perhaps an anomaly will emerge that resists all conventional explanation, forcing a revision of history. Or perhaps the mystery will persist, a question that fuels curiosity rather than closure. In the end, the possibility of ancient intelligence on Pangaea serves as a mirror. It reflects our own condition, brief, energetic, uncertain. We build, question, and imagine, aware that time will one day fold our works back into the planet. The rocks will hold only hints of our passage, just as they may hold hints of others. Whether or not those hints ever resolve into proof, the act of looking connects us to the deep continuum of life and change, reminding us that we are not separate from Earth's story, but a momentary expression of it, thinking about itself before returning to stone.